All right, I think we can start. So yesterday we did the introduction to STM, and today I'm gonna be talking to you, taking some further steps. But first, let's do a bit of a recap of what we've seen yesterday. So STM is optimistic concurrency control. They have this thing which is called a TMVAR, a transactional variable, and operations on these variables are called transactions. And you can run transactions using atomically and combine them with or else. This is all stuff we've seen. And as the second part of the recap, these transactions get rerun on conflicts, and we know because we keep a log. I still haven't mentioned anything about this log works, but we're going to do that on Wednesday. And you can also call retry to run your transactions yourself. And the runtime reruns transactions when their inputs change. And you can use this retry thing to implement blocking operations, and this is one of the things we're going to see today. So, by request, we're going to use TMVAR as a piece of Lego to build some more complicated data types, and we're going to implement those ourselves. And we're going to try to create some of the data types which are in STM in the library, and I'll just copy and paste. I've copy-pasted the STM library source code, and I'll walk you through it. And if we have some time, we can take a look at STM containers, which is a library with some additional data types. And I have, I'm going to talk about the problem that solves in a bit. And this is all other people's code. I haven't written any of this, but I'm trying to walk you through it so you might understand how it works, because I think it is very interesting. So, transactional Legos. TMVARs are nice. We've done some things with them. If you did the exercises, we've done some transfers and bank accounts. And if you also looked at the exercises, at a certain point, you want to build some other data types. Certain situations call for this. Sometimes you want a queue, or you want a queue with a bounded length, or you want something which seems like a lock. And the STM package library provides a bunch of them, and we'll see how they work. So the stuff that's in STM. There's TMVAR for variables. These are actually implemented in the runtime, but the library contains some convenience functions to work on them. There's TArray for arrays. There's TMVAR, which is a variable which is either empty or full. There's queues and bounded queues, and also channels. Channels are slower than queues, but support broadcast things. So
M is for maybe, or?
Yes. We'll see in a bit. Let's see. I'm going to discuss TMVAR queues and the bounded queues. The channels I'm gonna leave because they're very similar to queues. Yeah, that's it. So TMVAR, right? A TMVAR A is either empty or filled, and the name comes from MVAR, which because that's also a thing that exists in Haskell, and I'll discuss similarities and differences in a bit. And it can be used as a synchronization primitive. So imagine you have an application which depends on a database connection pool, and you only want to run actual database transactions after the connection pool has been initialized. You can put the connection pool in TMVAR. If it's empty, the configuration or the pool hasn't been initialized yet, and if it's full, namely with the connection pool, you can use the connection pool in order to do database requests. And this is the API. It's not the entire API. There's some other convenience functions, but these are the ones we'll look at. We can create new TMVARs. We can create new and provide an argument with which they are filled. We can create new empty TMVARs, and we can put and take on a TMVAR. And both of these, put and take, are blocking operations. So put, if it's full, if the TMVAR we're putting on is full, it will block until another thread empties it. And take will block until the TMVAR is full. So it's basically, you can also think of this as a single element queue, right? This is the API. Are there any questions about the API?
If TMVAR is full, can we put another value?
You can put another value as soon as the TMVAR becomes empty. So this will wait until another transaction reads the TMVAR, so it becomes empty, and then put will succeed and populate the TMVAR again. So, and this waits until there's an actual element to read out of the TMVAR. Is this clear? All right, cool. The question is, can we build these ourselves? And the answer is yes. And we can even build them in Haskell, which I think is great. It's basically a TVAR maybe A, as someone in the audience mentioned. And this is really cool. We can use the TVAR as a piece of Lego, as a building block, to build some more involved structures. So let's just add a new type wrapper around this, and that's the actual implementation that's in the STM library. So let's see how we might implement this. We add the new type, which we saw on the previous slide, and create a data constructor, and within this data constructor we have a TVAR maybe A. And if we want to create a new one, we pass in the initial contents if we want to do so, and then create a new TVAR and put the just in there, and then inner has type TVAR, and we wrap that in TMVAR, and we use pure because we're in an STM transaction. Right? Cool. And the empty one is the same, but with nothing instead of with just. Oh. Nothing really earth-shattering, but it's good to see that you can take the TVAR as a building block and do other stuff with it. Right? So putting into a TMVAR, which is slightly more interesting, we pattern match and get the inner TVAR out of our TMVAR, and we have an argument for the new contents. So then we read the current contents. If it's already populated, then we block, which we do using retry, which is the retry this transaction until it succeeds part of STM. And this will keep on retrying the put operation until the TMVAR is empty. In the nothing case, it's empty, and we can write it, and we need to do some wrapping and then return a pure unit because we're in STM. Any questions about this? Cool. Take TMVAR is reading from it and leaving it empty if we can actually read from it. Same story here. We unwrap, we read the contents, we match on maybe on the maybe contents. If it's nothing, we retry. If it's a just, we write nothing and then return the contents of the maybe. All right, cool. So that's basically the API. There's some other convenience functions in there that you might use. Like there is a peek-like operation where you can read the contents but leave the variable populated. It's and there's a bunch of other utilities. This is the gist of it. So I mentioned TMVAR before, and we now have a TMVAR, right? What's the difference? Well, for instance, there's a T, right? But besides that, they're defined in or accessible from different modules. The MVAR is in control concurrent MVAR, and the TMVAR is in control concurrent STM TMVAR. But that doesn't tell you anything about the semantics.
First name stands for mutation.
They have similar semantics, as in the MVAR is also either empty or full, but it's from a bit earlier research. Namely, the MVAR is from this paper called Concurrent Haskell in 96, sorry, and TMVAR is from composable memory transactions, and this should tell you a bit about their lineage. So MVAR is from an extension to the then Haskell, what was Haskell back then, that introduced concurrency primitives, and the TMVAR is part of STM. And they have slightly different semantics. Namely, MVARs have fairness, which is important. And TMVARs have no fairness guarantees, like the rest of STM, because TMVARs are implemented using TVARs, and TVARs are just STM, and we've learned already that the STM fairness is basically, it's random. It's whichever thread happens to be able to commit. So the MVARs here have, in what I could gather from the documentation, most implementation have first come, first serve fairness. But the specification says that no thread can wait indefinitely on an MVAR unless it's held indefinitely by another thread. So if there's a deadlock until then you're out of luck, but otherwise every thread is guaranteed to get access to this MVAR. And this means that if you have starvation and fairness problems with your STM, you might want to not use STM, but use variables which are concurrent, but provide fairness. All right, any questions about this?
MVAR is just, they live in simply IO monad, or there's some?
Yeah, it's the IO monad, yeah.
Just IO monad?
Yeah. Yes.
Did you somehow build your own fairness on top of STM?
That's a good question. I have a feeling that that might be difficult. But you can architecture applications in such a way that you work around the scheduling. So fairness guarantees, if you need it, if you find out you need it, use that. No fairness guarantees. It has the more ergonomic STM interface. The problem here is like all the stuff we've seen in the introduction, where you have the niceness, like the rollback of and the atomicity and that kind of stuff. You have to take care of that yourselves. So that makes using that more involved. But if you're having problems with scheduling and that kind of stuff, or contention, sorry, then it might be worth looking into. And the documentation advises you to only use those when you need it, and you know for sure you need it, and use these if you want a convenient interface with all the transaction rollback stuff. So I'm just going to copy that advice. Right. So these are a lower level tool, and they can be used against starvation, and this has the high level convenient STM interface, basically. All right. So those were MVARs. Let's do queues. right? A TQA is an unbounded first in, first out queue. So you have conceptually a big list of elements. You can put stuff in here, and you can write stuff here. You can read stuff here, and all the stuff goes in first come, first serve. These have order 1 inserts and reads, but it's amortized, which means generally over a sequence of n operations, each individual operation on average has, worst case, sorry, has O1 complexity. But single individual operations might have larger complexity. And we'll see where this comes from when we implement this. Right? So our interface, we can create new queues, like we've seen before. We can create new TMVARs, we can create new TVARs, and we can write and read to and from it. Read blocks if the queue is empty, using retry, as we'll see in a bit. So, can we build a TQ ourselves? Yes. And we can do so using 2 lists, as a matter of fact. One for the reading end and one for the writing end. So the data type looks like this. So there's 2 lists, one of elements in which elements are written to, and one in which there are elements waiting to be read. And you might ask yourself, well, if there's one place where things are written and one things where things are read from, how does the list that's about to be read get populated? We'll see in a bit. Any questions about this? Convinced? All right, cool.
Maybe why there are 2 lists?
Ah, that's a good question. That's to avoid contention. So you don't want, generally what happens with queues is there's multiple things writing at the same time and multiple things reading at the same time, or at least reading and writing happens at the same time. And if this is happening at the same time, you don't want to have those operations conflict. You want to be able to empty your queue quickly. So that's why there's 2 lists. It's to avoid contention. Right? Cool. So in this case, we use data instead of new type, but hey, we create a new queue. And we do so by creating a TVAR for the read end and a TVAR for the write end, and then returning that in our data type. Right? Cool. I've duplicated the data type right here. That's just for your convenience. Writing to a TQ, well, we don't need the read end. So I use an underscore to signal that. The type is a queue, and we write an element to it, and we do so in an STM transaction. So we need the write end of the queue, and which this has type TVAR list of A's. And then we read the TVAR, which we can do because we're again in an STM transaction, and then prepend our element to be written, which is O1 operation, order 1 operation, and then we write that into the TVAR again. Any questions about this? All right. Reading from a TQ, is the font size okay? Okay. Here we need the read and the write ends. In this case, we first, and the reason we do this will become clear in a second, read, this again has type TVAR list of A's. we get the list of A's out of the TMVAR and then see if there's anything in it. If there's anything in it, then that's good. We take the first element out, and then the tail goes back into the TMVAR and we return our element. And now the question is, what should go here?
You would invert the swap rate.
Mm-hmm. Yeah, so you swap and reverse. Oh, oops, sorry. We get the contents of write, we reverse them, and store it in read. And we retry if write is empty, because in this case our queue is completely empty. This is where the amortized comes from. Because this is a linear operation in the length of the write queue, but amortized because the write queue can only grow as large as the number of elements you've put in it. So over a sequence of, and you can only read as many elements as you've written. So over a sequence of n operations, you write n times and you read n times, and the reads and the writes are constant, and the reversal in every case is bounded to n. So if you average this all, you get amortized constant time reads and writes. Is that clear? Cool. So I'd like to show you the code, but or your question might be, why isn't there still any code on this slide? And that's because I'm going to make you write it, and that's going to happen on Wednesday morning. Cool. An observation here is that this queue is unbounded, right? It can contain an infinite amount of elements, or at least an amount of elements which, however many we can store in our memory. So sometimes you want to add bounds to a queue. And a bounded queue is a queue with a configurable capacity. If the queue is full, because there's as many elements in it as there is capacity, then we block. And this can be useful for implementing back pressure. So let's see. As an example, we might have some weighing a work ingestion mechanism. Like we accept HTTP calls, and each call will mean that we have to do some processing, and the processing can be expensive. We might not want to allow for an infinite amount of work left to be done, but at a certain point signal to our client, hey, wait a minute, slow down, as a blocking operation. In that case, you can, for example, issue an HTTP response in which you say, hey, slow down a bit. Or you can just leave the HTTP request processing going on for a very long time, however you want.
Can I have a question?
Yeah.
Sure, what's the difference between queue, TQ, and just a single TMVAR? Because actually you said that when you have a TMVAR and when it's full and some process is trying to write,
Mm-hmm.
you get the blocking.
Yeah.
And so in a way, isn't this blocking kind of like queue, because a number of, let's say, processes,
Mm-hmm.
friends are waiting for the possibility to write, right?
Mm-hmm.
So isn't it really a kind of a queue behind this blocking?
You mean the TMVAR?
Yeah.
Yeah, the TMVAR you can think of as a single element queue, but you might not.
Yeah, but actually there is, in a way, there is a infinite, a queue of infinite number of elements, right? Because
The TQ, yes.
no, I'm talking about TMVAR. TMVAR.
Yeah.
You can put multiple things to a queue and it will block.
Yeah, so the idea here is our queues, we have generally in these kinds of systems, you have a capacity of the stuff you can process. And generally it's more than one, right? And another thing which happens pretty often is a queue is either empty or it's full. Like the intermediates, if a queue is getting filled faster than you can take items out of it, it will be full really, really fast, right? So if you have less capacity for processing items.
Okay, I'm not asking about this capacity, yeah?
Mm-hmm.
Just step back.
Yeah.
I'm just wondering whether you really, why actually do you need a queue, a TQ?
Oh, because, yeah.
The TMVAR in itself, there is a kind of a queue behind TMVAR.
True.
Right?
But the TMVAR means you can only process single elements at a time, and this allows for multiple readers, multiple writers, which process different amounts of elements. And as long as your processing goes fast enough, this will work, right?
So Q is about introducing Q. TQ is about the speed, or there is some.
Yeah. In some cases, yes.
First thing for your application, you might be able to have the burst for the size without introducing blocking.
But it's all. But Q is introduced.
It's not just about speed. If you have a reader which combines multiple items, for instance, it's a fold.
Yeah.
It takes two items and combines them.
Okay, that's okay.
That will not work if you have a single place queue.
Right.
All right. That's also a thing. Thank you. Good argument. So we can use this for back pressure in our systems and also for more advanced combining stuff. So this is, the combining stuff is an argument for queues, and the bounding is an argument, back pressure is an argument that we might want to add bounds. So, how do we add bounds to our TQ? Well, we need to know not really the sizes of the read and write lists, actually. That's sort of false. We need to know the capacity left in our queue. And we can do so using two counters, and I'll show you. For every insert in our queue, if we know how much, in the simple case, if we know how long this list is, right, and we never read from it, then the length of this list determines it determines how much we can still write to our queue. If we start reading elements, we remove stuff from the queue, and that frees up our capacity. That's the basic mental model you have. Like, you can have, let's see, you can have a queue that's completely full and have 5 elements which have been read, and then balance those out, and then you have still 5 capacity left. That's the basic idea. So we maintain counters for read capacity and write capacity, and we still have our lists which specify like the stuff, the read and the write ends of the queue. So if we want to create a new TB queue, we need a parameter for the size. We create our lists like we did before. The read thing is 0, and the write thing is as large as the size is. And then we put this in our abstract data type. These counters and stuff, they will, you need to see how they get manipulated by the read and the write functions in order to be convinced by their correctness. So, if we want to write to a queue, we need to know if we still have space for elements to be written, which is called W size, write size. We read this from our TVAR int and then check if it's not equal to 0. If it is not equal to 0, we still have some write capacity left. So then we're in this branch. We decrement our write capacity, and then afterwards we jump right here. So we decrement our write capacity, and this is a strictness annotation, which is important for performance, but not really relevant here. And then, so if this W is unequal to 0, we still have capacity, and we can just write to our queue, and we do so in the same manner as we did before. Otherwise, we need to figure out if we have read capacity. So that means this is the case where we have written items to our queue. Let's say we've written 10, our queue has capacity 10. Then W will be equal to 0, meaning we don't have any write capacity left. But we might have already read 5 elements out of our queue. So that's why we need the read capacity number. And if we have some read capacity left, we can swap the read and the write capacities and subtract 1, and that gets us our new write capacity. Items have disappeared from the queue. Let's see how this looks in code. We read the amount of read capacity we have left. We do the same check. Like if that's if this is 0, then we need to retry. We need to block. We don't have any write capacity, and we don't have any read capacity. Retry. If it's unequal to 0, we can set our size to 0 back again, and say we have enough write capacity again. The items will have disappeared from our read end of the queue, so we can swap around with these capacities. And again, we have a strictness annotation here.
Question, have you told me about thread scope yet?
Nope.
Okay.
So we have this.
Why do you need to strictly evaluate that?
This means, yeah, we don't need this func any later. So we don't need to share it, and we can just compute it straight away.
So for performance.
Yeah, it's a performance thing. And in case you're wondering about laziness in Haskell and how you can force strictness, there's a couple of forms an expression can be in different stages of evaluation. They have different names. This thing evaluates an expression, so this will not be stored as this expression, but it will just take the value of this r and subtract 1 and compute that straight away. Otherwise, we end up with a bunch of memory overhead. So this is, and the same goes here, right? So it's a performance thing indeed. Yeah, this is writing to a queue. I don't have reading from a queue because it's really the same thing as before. I'm not gonna really bore you with it. It's basically see if there's stuff empty, reverse things otherwise, and maintain these counters. Instead of decrementing, we increment. Every time we read, we increment the read capacity counter, and that will ensure this goes all right. And this is, again, something we're going to do on Wednesday. So, nice. How am I doing for time? Oh, I'm going way too fast.
I have a question.
Yeah.
Why do we have counters? Couldn't have we one counter with total number of everything on the both lists?
That's again the contention argument. So you want to have asynchronous, or you don't want the parts that read and the parts that write to introduce conflicts to the same TVARs. So that's why they're separate, and we only combine these two numbers in the case where we're out of capacity.
Right.
And that's, again, a performance. Right. So, as a final closing, because it's going way faster than I anticipated, let's do some STM container stuff, right? Sometimes you want a hash map. Sometimes. Try to not do this if you can avoid it, but sometimes you do want this. It can be useful whenever a hash map is useful, like user ID to rate limiting information, or something else. And if you want this, and you want this in your application, you might be inclined to take the same Lego approach as we've taken thus far, and take a TVAR, take a hash map from container stuff, and then put TVARs in there.
Why are you using TVAR device?
Because you want to be able to update individual elements if they're already in the hash map. So if a key already exists in the hash map, you might want to change the value, the thing the key points to, without updating the entire hash map. So then there's a TVAR there, so you can mutate the individual cells. But this entire thing, in general, is not very ideal. And can you tell me why? I'm sorry?
You have to look at the map.
Yeah. Yeah, exactly. Every time you, for updates to individual keys are fine. That's what this TVAR is for. But if you update the structure of this data structure, if you update, add a new key or remove a key, then this outer TVAR will be marked as changed. And so updates to the entire hash map change the outer TVAR, meaning anything which inserts new keys contends with anything else which inserts new keys. And for some workloads where you have lots of updates to the structure of this thing, this might impose a bottleneck. So you get contention on key addition and key removal. Changing individual keys is fine because there's only one thing that gets marked as changed there. But adding new stuff, it marks this entire thing as changed. So that's the reason. We want to decrease this contention again. And this requires splitting the workload into some chunks, right? You want a mechanism to avoid having to mark the outer TVAR as changed every time you do a key update. And this basically means we need to go on a lower level. And it basically, in the case of the STM containers library, it means implement map again, or the backend. And there is this thing which is called a hash array map tree, or trie. There's different kinds of pronunciation, which is a way of implementing maps. And I'm gonna give you the gist. I'm not gonna give you the code, because the code is very big. So this is a bunch of words, right? But the basic idea is this. You hash each key, and it yields a binary value. So you have a big binary string. And then you store the value in the tree at the location determined by the hash. But I can imagine that's not very helpful if you don't know what a tree is. Before I give you the picture, let me give you the idea. Basically, each key is a string of bits. And a tree is a way of encoding this key using prefixes. So we have different levels in the tree, each which stands for a prefix. And if you walk through the entire thing, no, wait a minute. If a prefix has only a single value associated with it, then there's a pointer to that value. If there's multiple ones, there's another level. That's the basic idea of a tree, or trie. I don't. There's two pronunciations. I don't know which is more common. And if you want to get a proper introduction to this, there's this, which is pretty good. So in pictures, right? And the picture credit is from the same person. This is what I just mentioned. We have our root node, our first level, which in this instance takes a look at the first 2 bits of our hashed key. In this case, there's only one value in our map, which has a hash which starts with 0, 0. So we put a pointer to the value immediately. In the other case, where you have a bunch of other stuff, namely these 2 values, we need 2 more levels. And then, so if you wanna follow this, like the key with hash 1 1 1 1 1 1 1 0 ends here. 1 1 1 1 1 1 1 1 1 1 ends here. That's the idea of a tree, but there's a problem with this, which is all these null pointers and all these extra elements, and there are some ways to that you can compress this stuff, but that's all here. Yes?
What's the point of doing that, since hash should be distributed evenly on all the numbers? So we don't have any performance gain here, I believe. Or we do? What's the point of having this data structure?
Yes. That's right now. You can imagine that if you previously we had a TMVAR Hashmap TMVAR A. Here we can be a bit smarter and a bit more granular. If you take every box here and make that a TMVAR, and everything here and make, or let's see. I don't know how the TMVARs are distributed exactly, but if you observe that you can if you change these pointers to TMVARs, you can observe that you can add new keys to this map and remove keys to this map, which without locking the entire thing, right? You only have to change this value in order to add a new key to the map. Namely, you have to, in this case, you can insert a value right here. Or you can change this and have another neighbor right there. And then you get, then this is better, right? You don't have to lock that, you can just lock this. And I use the term lock, but it's not lock. It's introduce contention here is better than introducing contention there for everything. And that's the gist of this. So you can imagine this is better. Like updates to a part of the map are not almost isolated, are more isolated. And when we sometimes need to insert new levels, but it's way, way, way better than global contention. If you manage to compress this, right? And you can do all sorts of bit fiddling tricks with masks and that kind of stuff. And there's a really cool paper. It's called Ideal Hash Trees, which describes this data structure. And a real implementation is obviously more involved and has compression and a few other things. This is work by Nikita Volkov, and they wrote a nice blog post detailing the reasoning for choosing this. And it's basically what I just told you, but with some really cool benchmarks, and that's worth checking out. So as a summary, unless there's questions about this. As a summary, we have TMVARs, which are TVAR MABAs. We have TQs, which are TQs, TVAR list of A's, TVAR list of A's. If you want bounds in your queues, you can add counts for read and your write capacity. And the SDM containers package provides a whole bunch of, like 5 or something different data types, all based on this hash array map tree. And this allows you to have containers which you can share over multiple threads, actors, SDM writers, without any contention when you have structural updates. So this is my stuff for today. And tomorrow, the first hour, which is at 10, we're going to do exercises. And if we still have some time, we're going to still do some exercises. If you want to do that, you're very welcome. I'll be here. If you're not, then that's obviously fine too. You're the judge of your own learning. And you can get some more sleep, or you can attend another talk. And then finally, we're going to do some implementation notes and discuss the semantics of SDM, and we're going to do some logic and mathy looking stuff. Sounds good? All right, then that's it from me. Today, if you have any more questions about those exercises, I'll be here for just a bit. I'll update them for tomorrow, I think, slightly. And yeah, that's it. Cheers. Thank you for your attention.